We like to believe slow dashboards are a tooling problem, that a bigger warehouse will magically fix them. But most performance issues start with something simpler: bad data models that push heavy work into every single query. If you're still hitting raw events and hoping it scales, this episode is for you. I'll show you 4 production-grade modeling patterns that keep pipelines fast and bills predictable. No hype, no vendor worship, just the design decisions that stop your system from collapsing under its own data. Setup: why modeling mistakes break pipelines at scale. Okay, let's set the baseline. The core idea is this: models decide where the work happens at query time or design time. When the model is vague, every dashboard, every analyst, and every downstream job pays the price in compute, latency, and rework. It's death by 1,000 full scans. What this looks like inside a real company is familiar. Teams point BI tools at raw event tables because we can always aggregate later. It works in development with 1 million rows. Then usage grows. The same count distincts and multi-join rollups now hammer billions of records every morning. Queries queue, dashboards miss SLAs, finance asks why the cloud bill doubled, and the governance dashboard says everything is fine. The company usually isn't. The reality is engines today are fast. MPP, columnar storage, caching, these aren't your bottlenecks most of the time. The bottleneck is pushing repeated predictable work onto ad hoc queries, forcing the warehouse to solve the same puzzle again and again. That's a modeling problem, not an engine problem. Most people think we're doing ELT, we'll optimize later, but schema on read without a semantic plan becomes schema on regret. You end up with inconsistent metrics, ambiguous joins, and a constant scramble to explain why 2 dashboards disagree about yesterday's revenue. And once users lose trust, they stop using your platform and go back to spreadsheets. That's not just annoying, it's a sign your data product failed. Now here's the uncomfortable part. Broken pipelines often aren't broken because jobs crashed. They're working but slow, costly, and semantically inconsistent. Slowness is a symptom, so are runaway costs and brittle joins. The cause is upstream: granularity, relationships, and where you place computation. Speaking of clarity, if you're responsible for a production system, this difference matters. We're going to move specific, repeatable work out of ad hoc queries and into durable, tested models. You'll hear 4 patterns. Each one shifts labor from every query to scheduled, predictable jobs. The payoff: seconds-level dashboards, stable costs, and a data team that spends time improving the business instead of firefighting. Let's start with the most common fix you can implement this quarter. If you remember only one thing from the setup, it's this: move repeated, predictable work out of ad hoc queries and into durable, tested models so the warehouse stops solving the same puzzle on every request. Mistake number 1: skipping cumulative tables. Why dashboards stay slow. Most BI teams make the same mistake. They compute important metrics from raw data every single time. Here's what actually happens. Every morning, your dashboards scan events, join with dimensions, deduplicate, and roll up to daily numbers. That's like recalculating your entire banking history every time you check your balance. It works on day 1. It collapses at month 12. Cumulative tables solve this by front-loading the work. You pre-aggregate once, store the result in a stable structure, and refresh on a schedule. Instead of millions or billions of rows per query, your dashboards hit a small partitioned table with 1 row per date, per segment, or per whatever your consumer filters on most. The warehouse does less work per request. Your users get fast answers. Your finance team sees predictable spend. Let's break that down. Daily active users, revenue by day, orders per region. These are canonical rollups. They change incrementally, not retroactively. So don't ask every dashboard to rediscover them from raw clickstream and order lines. Create cumulative tables. Define the grain. 1 row per day per segment you care about. It's the key product region. Compute the metric once in a scheduled job. Store last updated to signal freshness and enable downstream cache invalidation. Partition by date, so reads prune old partitions quickly. Cluster by frequent filters like region or product category to keep scans tight. Now here's the reality check for production systems. Cumulative tables aren't nice to have. They're the difference between usable BI and an expensive science experiment. In practice, this usually means you maintain 2 layers: raw events for traceability and feature engineering, and cumulative tables for BI and near real-time reporting where exact second-by-second freshness isn't necessary. A quick war story. On a growth product, we had daily KPI decks that pulled count distinct user ID from raw events. It passed UAT with a month of data. 3 quarters later, Monday mornings meant 2 to 3 hours of red dashboards, analysts copying SQL into spreadsheets, and a finance review derailed by "Why is DIU different here?" We introduced a user's daily table with 1 row per day, region, and product. We made today's partition idempotent, yesterday immutable, and added last updated. Result: load times dropped to seconds, incident pings fell off, and finance stopped filing doesn't match tickets. Nothing magical, just move the work once instead of every time. And you probably think, what about freshness? Won't these get stale? Yes, by design, that's the trade-off. But most business KPIs don't need second-by-second updates. They need consistency. If your stakeholders truly need minute-level accuracy, you can add a short rolling job that increments today's partition more frequently while keeping historical partitions immutable. Today's slice can refresh every 5 to 15 minutes. Yesterday and earlier remain fixed. Another concern, what if definitions change? That's why the logic lives in code with version control and tests. When a metric definition evolves, you backfill affected partitions. Cumulative tables make that backfill explicit and auditable, rather than hoping every dashboard author updates their SQL in lockstep. In production settings, this means less drift and fewer "why doesn't this match finance" threads. A quick micro story. A team complained about 60, 90-second dashboard loads and surprise warehouse bills. They were counting distinct users across a multi-billion row event log daily. We introduced a daily user summary table with 1 row per date and segment plus last updated. Queries dropped to seconds. Scan volume fell off a cliff. Spend stabilized, no change in vendor, just moving the work. Another real failure, we tried to optimize later by pushing a complex distinct into the semantic layer. It hid the problem, not the cost. Every dashboard still executed the same heavy logic. The fix was the same: cumulative tables owned by the pipeline, tested and versioned. Afterward, the semantic layer simplified to simple selects, and the help desk tickets about stale data vanished because freshness was explicit on every row. But here's where it gets interesting. Design your cumulative tables to match consumption. If your most common cut is DIU by region by product, include those columns at the grain. Don't force BI to join back to white dimensions on every request. If you need the dimension attributes for display, include stable keys and only the attributes that are slow changing or required. Everything else can be joined selectively, not by default. Now, a few practical rules to keep you from shooting yourself in the foot. Always include last updated and, if helpful, a data valid from and data valid to clarify what the row represents. Partition by date, it's the most selective predicate you'll have. Cluster on the fields most commonly used to filter or group like region, product, plantier. Keep the table narrow. Only store what's needed at that grain. Extra columns bloat storage and hurt compression. Make today's partition idempotent. Your incremental job should be safe to rerun without duplication. Let's address skepticism. Aren't pre-aggregations rigid? They're focused. That's the point. They serve the high-frequency questions cheaply. For one-off exploration, analysts can still go to curated fact tables. But don't force every routine dashboard to pay exploration prices. What about late-arriving events? 2 tactics. 1. A small lag window. Compute yesterday's final numbers this morning to capture late events. 2. Rolling correction. Allow a short backfill on recent partitions, say the last 7 days. Both are common in production and keep totals accurate without reprocessing entire histories daily. What if we're in a streaming world? Cumulative tables still work. Your stream updates a hot partition in near real time and you roll those up into the daily summary. The same principles apply. Explicit grain, partition by date, visible freshness, idempotent rights. Finally, governance. Centralize metric definitions in the transformation code, not scattered across dashboard tools. Document the metric, its grain, and its update policy. Expose a semantic layer, if you have one, but don't let it mask sloppy upstream logic. This is a finance decision as much as a modeling decision. Every extra full scan is a line item on your bill. The takeaway for this mistake is simple. If a metric is used daily, pre-aggregated, move compute from ad hoc queries to scheduled builds. Your dashboards get fast, your costs get boring, your team gets time back. If you remember only one thing from this section, it's this: pre-aggregate high-use metrics into cumulative tables so you pay once in a scheduled job, not forever on every dashboard query. Once you feel that speed difference, you'll see the pattern. We aren't making SQL prettier. We're changing where the work happens. That shift is how you keep systems reliable as data and teams grow. And it sets us up for the next failure point: fact tables, where most warehouses silently die. Mistake number 2, broken fact table design, grain, keys, and partitions. Everything changes when you answer one question clearly. What does one row represent? That's the grain. If you can't say it in a clean sentence, your fact table will lie. 1 row equals 1 event, or 1 row equals 1 order, or 1 row equals 1 session. Pick one. If you blend them, events mixed with sessions mixed with users, you'll spend months debugging phantom churn, duplicate revenue, and joins that never quite reconcile. Let's break that down. Say your product analytics table sometimes records page views and sometimes tries to summarize sessions in the same place. You join that to revenue at user day because it kind of works. Except now your KPIs drift. Your conversion rate changes depending on which analyst wrote the query. That's not a query problem, it's a grain problem. The reality is your downstream logic can't be stable if the upstream meaning of a row is fuzzy. So start with a grain declaration in plain language. 1 row equals 1 session, bounded by start time and end time. Great. Now, derive everything from that. A surrogate session ID, the user ID foreign key, the source medium at the time of session, and any session level metrics you need at this grain. Events live elsewhere, orders live elsewhere. If you require a different analysis, you create a different fact with its own explicit grain. Which brings us to keys. Most people think natural keys are cleaner. User ID plus timestamp equals unique event. It feels elegant until you hit scale. Natural keys fluctuate, collide, and are hard to index across partitions. Surrogate keys exist for performance and operational sanity. Use a generated integer or UUID as the table's primary key. Keep natural keys as attributes and foreign keys for joins. This gives you stable deduplication, simpler lineage, and faster point lookups. In practice, this usually means a two-tier key, a surrogate primary key for the fact itself, and a composite uniqueness constraint implemented in your transformation code to prevent duplicates from source variants. A hard lesson. We inherited a clever facts design. One table mixed events and session summaries with a natural key, user-id event time. It worked until daylight savings, retries, and upstream replays created collisions. Analysts started seeing negative churn and double-counted revenue. We split the model, one fact per grain, events, sessions, orders, added surrogate keys, and enforced uniqueness in transforms. We also partitioned by event date and clustered by user-id hash. Outcome: duplicate bugs disappeared, query times fell, and we stopped firefighting. Why does conversion change when I add this join? Now partitions, this is where cloud bills explode. If your large facts aren't partitioned on a selective time field created at event date, order date, you're paying to scan history on every query. Partition by the time dimension that most queries filter by. Then cluster by secondary predicates, users apply often, customer id hash for skewed customers, region, or product category. Time-based partitioning lets the engine prune 99% of files instantly. Clustering keeps the remaining scans tight. The finance impact is immediate. Fewer bytes read, fewer credits burned. A production reality check. Most slow warehouses aren't suffering from engine limits, they're suffering from lazy grain and missing partitions. Inside a real company, you see this as a dense DAG of transforms feeding a huge unpartitioned table called events all. Everyone queries it because it has everything. Everyone also complains it's slow. The fix is not a bigger cluster, it's multiple facts at clear grains, each with time partitions and sensible clustering, plus a semantic layer that routes common questions to the right table. War story. Cloud costs doubled in a quarter with no traffic spike. Root cause. No partitioning on a core fact. Every KPI scanned years of history. We added date partitioning, clustered on region and product, and tightened the semantic defaults. Result. Scans dropped by an order of magnitude and finance finally got a stable forecast. No heroics, just modeling basics applied late but consistently. Let's talk joins. Once your grain is crisp, joins get safer. Facts join to dimensions by stable surrogate keys. If you need many-to-many relationships, orders to promotions, users to features, don't hide them in array fields in the fact. Model bridge tables at their own grain. One row equals one order promotion link. This prevents accidental double counting when you roll up. If you must store arrays for convenience, mark them as non-canonical and don't use them for core KPIs. You might be thinking, do I always need surrogate keys? For high volume facts, yes. In lower volume, natural keys can work, but add a synthetic key anyway for consistency and future proofing. As a baseline standard in production systems, consistency beats cleverness. What about late arriving records and updates? Designed for idempotency, use merge semantics keyed on your surrogate or composite unique fields so reprocessing a batch won't duplicate rows. Keep a load timestamp and a source record hash to detect changes for type 2 dimensions or late corrections. In practice, this usually means your incremental job upserts today's partition and optionally a recent backfill window while historical partitions remain immutable. A quick example, a team modeled transactions with one row per user per day because it made early dashboards simple. As requirements grew, refunds and multiple orders per day wrecked accuracy. We split it. One fact at transaction grain, one at daily user summary grain, clear surrogate keys partitioned by transaction date, clustered by user ID. Query times dropped, costs stabilized, and finance stopped asking why two dashboards never matched. Guardrails to remember. If you can't describe one row in one sentence, your grain is broken. Every large fact table needs time-based partitioning by default. Use surrogate keys for facts, keep natural keys for joins and audits. Model many-to-many with bridges, not hidden arrays. Make increments idempotent. Late data should correct, not duplicate. That's the foundation. Get grain, keys, and partitions right, and you stop paying the penalty on every query. Get them wrong, and no amount of tuning will save you. Speaking of penalties, our next pattern deals with time itself and how to avoid row explosions when activity spans ranges instead of single dates. And if you remember only one thing from this section, it's this. Pick a crisp grain, partition by time, and use surrogate keys. Clarity here turns slow, costly joins into fast, predictable queries. Mistake number 3, modeling time with row explosion instead of date lists arrays. Time is where otherwise clean models go to die. The thing is, most activity doesn't happen on a single date. It spans ranges, trials, subscriptions, campaigns, bookings, outages. When you model those ranges as one row per day, you turn a tidy dataset into a bonfire of duplicates. 10 million users on 14-day trials, that's 140 million rows before you even join to anything. Then you add segments, plans, and regions, and suddenly every query is a full-body workout. Let's break that down. The beginner move is to expand every active day into its own row so downstream queries can just group by date. It feels simple. In practice, it creates skew, slows scans, and magnifies errors. Any bug in the expansion logic multiplies across days. Any late arriving event creates backfills that touch huge ranges. And every join now has to match not just who and what, but also which of many duplicated dates it aligns with. Here's the alternative. Model the range as a single record with clear boundaries and a compact representation of the days inside. One row equals one continuous period. Store start date, end date, and an active dates array or bit set that represents the coverage. Now you've captured the same truth without spraying the table with copies. This is not just about elegance, it's about compute. You trade row explosion for a small, well-compressed payload the engine can scan efficiently. A production failure that made this clear. We pre-expanded subscription periods to one row per active day for convenience. While it ballooned a compact table into billions of rows, every late payment fix triggered week-long backfills. Queries slowed, bills rose, and small logic bugs multiplied across days. We refactored to one row per continuous period with start date, end date, and an active dates array. We added a bounded expansion view for the last 90 days. Backfills shrank to minutes, daily jobs stabilized, and analysts stopped building their own shadow tables. Where this shines is obvious. SaaS usage streaks, trial periods, subscription billing cycles, booking windows, rotating event schedules. Instead of one row per day, per entity, you keep one row per period. Downstream logic changes shape. You filter with date ranges first, date between start date and end date, then unnest active dates only when you truly need day-level output. That keeps most queries cheap and shifts the heavy expansion to the few places that demand it. Now, this is important because arrays come with their own trap. Unnest can be expensive if you treat it like a free lunch. Two guardrails keep you honest. First, always pair arrays with start date and end date so you can prune early with a simple range filter before expanding anything. Second, don't materialize daily rows unless a consumer explicitly needs them. In practice, that means providing two interfaces, a compact periods table for most analytics and a derived daily view built on demand for downstream tools that insist on flat days. A reality check. Inside real companies, analysts often want daily active users and push for pre-expanded tables because they seem easier to join. Resist that impulse. Provide a clean helper function or view that expands on a bounded window, say the last 90 days, so ideation stays fast while the core model remains compact. This is a finance decision as much as a modeling one. Every pre-expanded day is a cost you'll pay forever. Another painful episode, a growth quick win, created a daily expansion table joined into every dashboard. It seemed harmless until we had to correct a business rule. Recomputing that table slammed the warehouse and blocked other workloads. After moving to period-based storage with on-demand expansion, the same correction became a targeted job and concurrency issues disappeared. How do you handle overlaps and gaps? Normalize periods before storage. Merge adjacent or overlapping ranges for the same entity and reason code, so each row is truly a continuous spell. Keep a reason or status field to explain why the entity is active during the period, trial, paid, grace, paused. That preserves business meaning without extra joins. Finally, make it auditable. Include a period ID, load timestamp, and a source record hash. Late changes should update or split periods deterministically, not create duplicates. If you need daily extracts for BI, schedule a small job that expands only recent periods and caches the result. Most questions won't need it. When they do, you'll pay for it once, on purpose. That's the reality behind the model. If you remember only one thing from this section, it's this. Store time as compact periods and expand to days only on demand. Avoid row explosions that you'll pay for on every query. Mistake number 4, forcing relational joins when the logic is graph-shaped. Look, some questions aren't about rows, they're about relationships. Who influenced whom, which system triggered which other system, how fraudsters reuse devices, IPs, and payment methods across accounts. When you force these into star schemas, you get 5 to 7 hop joins, exploding intermediate tables, and pipelines that time out at random. The model isn't wrong because SQL is bad. It's wrong because the problem is graph-shaped and you modeled it as tables. The core idea is simple. In relational land, you compute relationships by joining tables. Each extra hop multiplies complexity and often the data scanned. In graph land, relationships are first class, the edge is modeled directly, and traversal cost scales with the path, not with full table joins. If your product questions read like, starting from this node, follow edges with these properties up to n steps, you're in graph territory. Let's break that down. Start with edges, not nodes. Most teams sketch users, devices, payments as entities. Fine, but the business logic lives in the connections. User, uses, device, user, pays with card, device, seen with multiple users, card, shared with multiple accounts. Those edges carry type, direction, timestamps, and weights. In a graph model, you define edge types with clear semantics and constraints. One edge per observed relationship instance with start time, end time, and a confidence score or count. Nodes become simpler, stable identifiers with essential attributes. The heavy logic moves to edges. What this looks like inside a real company is predictable. That fraud rules engine running on the warehouse is brittle. You're joining events to users, to devices, to IPs, to payments, then back to users to find rings. The SQL grows dense. You tune and materialize subqueries. It still crawls, and every schema tweak breaks 3 dashboards. Migrating the ring detection logic to a graph system, or a graph-like structure in your lakehouse, turns that mess into, from this user, traverse device, and payment edges up to 3 hops. Flag if we meet more than 2 risky nodes. The query's shape matches the problem. A sober story. We tried to detect account sharing with 5-hop SQL. It ran for tens of minutes, then failed under load. On-call hated it. We rewired the pipeline to model edges explicitly. User device, user payment, device IP with timestamps. So we computed a small set of graph features daily, shared device count, shortest path to flagged. Traversals for investigations dropped to milliseconds. And the warehouse stopped thrashing. The lesson wasn't graph saves the day. It was use graph where relationships are the product and project simple features back to tables for everyone else. But here's the reality check for production systems. Graphs are powerful and expensive to misuse. Don't reach for a graph because it feels modern. Reach for it when the relationship is the product. Fraud, recommendations, supply chain dependencies, system call graphs, org networks. If joins still answer the question cleanly at 2 hops, stay relational. The governance dashboard saying, "We adopted graph," won't help you pay the cloud bill. If you do go graph, constrain the blast radius, start with a narrow high-value subgraph. Model only the critical edge types and the smallest viable node attributes. Declare edge cardinalities and directions explicitly. For example, device observed on user is many-to-many, payment card used by user is many-to-many with fraud risk when degree exceeds a threshold. Service, call service is many-to-many with versioned edges per deploy. Include timestamps on edges for time-bounded traversals. Most production questions are, what's connected right now? Not what was connected 5 years ago. Data ingress matters. Ingest edges as append-only logs with idempotent upserts keyed by a deterministic edge id, hash of from node edge type to node time bucket. Keep source record hash and load timestamp for audit. Late events should adjust edge weights or time windows without duplicating edges. In practice, this usually means a daily consolidation job that merges edge observations, deduplicates and updates counts and last seen. Analytics interoperability is the next trap. Your BI tools still want tables. Provide 2 interfaces, 1 a graph store or graph engine for traversal queries, 2 denormalized relational projection tables for downstream reporting. For example, expose a risk scores fact, 1 row per user day with features derived from the graph, degree centrality, number of shared devices, shortest path to a known bad actor. This lets analysts work fast without learning graph query languages while the graph stays the system of record for relationships. Performance guardrails, bound traversals, enforce max hop counts and path uniqueness to avoid cycles exploding runtime. Pre-compute partial traversals for hot nodes, e.g. top risky devices, on a schedule. Don't discover the entire neighborhood on demand. Index by edge type and time window. Most queries filter by both. Cache common subgraphs for a short TTL if patterns repeat under load. Now the skeptic questions. Isn't graph overkill for our use case? Maybe. Prototype the core query both ways. If the relational version is simple, stable, and meets SLAs, stay put. We'll have to manage another system. Not always. Some lakehouse engines and warehouses provide graph functions or let you simulate traversals with adjacency lists. Start there before introducing a new engine. And the warning label translating every operational join to a graph because it's more general will slow you down. Graph unlocks problems that are fundamentally about connection patterns. Use it there. Keep everything else in dimensional or relational form. We learned that the hard way too. A team tried to move simple 2-hop product lookups into the graph for consistency. Traversals were slower than a well-partitioned relational join, and we added another system to maintain. We rolled it back. The heuristic stands. If joins are simple, stable, and meet SLAs, stay relational. The takeaway, when relationships are the heart of the question, model edges first. Let traversal be the primitive. Expose simple relational projections for everyone else. That's how you get near real-time fraud checks and recommendation features without turning your warehouse into a join labyrinth. That's the reality behind the model. If you remember only one thing from this section, it's this. Use graphs only when relationships are the product. Otherwise, keep it relational and dimensional for speed and simplicity. Synthesis, the pattern behind all 4. Now step back. What ties these fixes together? We moved work from query time to design time. Cumulative tables pre-aggregate once so dashboards stop solving the same puzzle daily. Fact tables force a crisp grain, stable keys, and time partition so joins are safe and scans are small. Date lists compress time ranges into compact periods so you pay for expansion only when a consumer truly needs daily rows. Graph modeling turns relationships into first-class edges, so traversal replaces multi-hop joins. If you think about it, each pattern narrows ambiguity. Grain clarifies what a row means. Partitions clarify where data lives. Arrays and periods clarify how time is represented. Edges clarify how entities relate. When meaning is crisp, engines can do less work, caches warm up, and costs settle into a predictable shape. What this looks like inside a real company is relief. Dashboards stop timing out, bills stop spiking, the on-call calendar goes quiet. Not because you bought a faster engine, but because you removed repeated work and encoded decisions close to the data. 2 closing guardrails. First, choose the lowest practical granularity you can govern, then build summaries for speed. Second, model the dominant access path. If most queries slice by date, partition by date. If most logic is about connections, model edges. Don't make every consumer rediscover structure that you could encode once. The uncomfortable part, this is less about tools and more about discipline. ELT won't save you if the model is vague. Semantic layers won't fix bad grains. Fancy warehouses won't rescue unpartitioned facts. You don't need heroics, you need choices that keep heavy work out of the critical path. That's the pattern. Shift compute upfront. Make meaning explicit. Keep hot paths cheap. Design for idempotence and audit. Your systems get faster, your costs get boring, and your team moves from firefighting to product thinking. That's the reality behind the model. If you remember only one thing from this section, it's this. Move compute to design time and encode, meaning at the model, speed, trust, and cost control follow. Career frame, how you grow as a data engineer. Your edge isn't knowing every tool. It's modeling clarity under pressure. You translate messy reality into crisp grains, partitions, edges, and summaries. You design for idempotence, audit, and cost predictability. You ask, where should the work live? Then codify it once, so everyone benefits. If you remember only one thing from the whole episode, it's this. Design models that remove repeated work from the hot path. Clarity in grain, time, and relationships is what keeps pipelines fast and costs predictable. One takeaway, shift compute to design time and make meaning explicit. Want more pragmatic, battle-tested patterns? Subscribe and watch the next episode where we turn these models into a governance-ready semantic layer. Clarity beats hype. I'll see you in the next one. That's the reality behind the model.